Maybe it's night where you are and everything around you has settled into stillness. Above your ceiling, past the soft haze of our Milky Way, another universe of light waits quietly, the Andromeda galaxy, drifting toward us through deep space. Tonight, we're exploring what your eyes can't hold, the scale of a star city so wide, so faint at the edges, it escapes ordinary imagination. We'll trace the hidden architecture of distance, follow the glow that has traveled millions of years to reach you, and uncover the invisible halo that stretches far beyond the bright disk. Because behind every point of light in the sky, there are patterns, motions, and mysteries unfolding in silence, delicate, ancient, and full of wonder. Now take a slow breath. Let your body soften, and together, let's walk gently into the darkness and see how vast the Andromeda galaxy truly is. So before we pin down a number for Andromeda's size, we have to agree on what big even means. With a coffee mug or your house, it's simple. You can set a ruler to it, walk completely around it, and take it all in at once. A galaxy isn't like that. It doesn't have a clean, hard edge. Instead, it fades away. Fewer stars, thinner clouds, dimmer light the farther you go. And that fuzziness forces astronomers to pick definitions. Think of Andromeda like a city seen from a plane at night. From the air you can see a bright downtown, skyscrapers and concentrated lights, then suburbs, then a faint glow from industrial parks, and finally isolated farms and the occasional highway light. Do you say the city is as big as the downtown core, the suburbs, or the whole metro area, including commuter towns? Each choice gives a different size. Here are the main ways astronomers measure galactic size, and what they mean when they throw out numbers like 200,000 light-years or 1,000,000 light-years. The bright disk, the part most of us picture. When people talk about a galaxy's visible size, they usually mean the luminous stellar disk, the region where most of the stars are crowded together and the light is bright enough to be easily seen. For Andromeda, that bright disk is on the order of a couple 100,000 light-years across. That's the part you'd be picturing if you imagine a glowing spiral edge-on. Observationally, astronomers often quote the diameter measured at a particular surface brightness level, for example, the so-called D25 isophote, which is a practical cutoff set by how faint the sky background is and how deep the image goes. The stellar halo and streams, the faint outskirts. When we look deeper with long exposures or star count surveys, we find stars well beyond that bright disk, a fuzzy halo of old stars, stellar streams that are remnants of smaller galaxies torn apart, and globular clusters out at great distances. These features push the visible extent of Andromeda far beyond the central disk. If you include the halo and tidal debris, Andromeda's reach can extend several 100,000 light-years, and sometimes people cite numbers approaching or exceeding 500,000 light-years for the detectable stellar population. The gas disk. Neutral hydrogen can be more extended than the stars. Astronomers map galaxies in radio waves using the 21-centimeter line of neutral hydrogen, HI. In many galaxies, the HI disk extends well beyond the optical disk, sometimes 50 to 100% further. For Andromeda, sensitive HI maps show gas stretching out a long way, And if you define size by the gas, you get a larger figure than the optical one. The dark matter halo, the gravitational boundary. And then there's the invisible part, dark matter. We can't see it directly, but we infer it from how stars, gas, and satellite galaxies move. The dark matter halo doesn't stop where the light does. It can extend 1,000,000 light-years or more, and sets the scale of the galaxy's gravitational influence. Astronomers often quote a virial radius, roughly the distance within which the galaxy's gravity has drawn in material and established a kind of self-contained system. For Andromeda, that radius is on the order of a few hundred kiloparsecs, hundreds of thousands to around 1,000,000 light-years depending on the definition and the assumed mass. Mass versus size versus brightness. 3 different big. It helps to separate 3 concepts. Big can mean bright, how many stars are packed into the center. Big can mean massive, how much total mass, including dark matter, the system contains. And big can mean spatially extended, how far out the material reaches. Andromeda scores high on all 3 compared to most galaxies in the local group, but the exact numbers change with the yardstick. Why the fuzziness matters in practice. Observational limits and choices bias the answer. Telescopes have finite sensitivity. If you take a short exposure, you'll only detect the bright disk. Longer exposures and targeted star surveys reveal faint streams and halo stars that push the size estimate outward. Different teams might use different isophotes or column density cutoffs, so you'll see a spread of published sizes, not because anyone is wrong, but because they're talking about different parts of the galaxy. A couple of concrete waypoints to keep in mind. When people say, about 200,000 light-years, they're often referring to the visible star-dominated disk, the region where most of Andromeda's starlight comes from. If you include the faint stellar halo and tidal debris, you're already looking at a much larger figure. And when you include the dark matter halo, the sphere of gravitational influence, the scale can grow by another factor of a few, reaching hundreds of thousands to 1,000,000 light-years. For a personal touch, imagine you're trying to measure the size of a fog bank on a cool morning. From the road you see the dense, low-lying part, and you might judge the fog to be a few hundred meters across. But if you fly above it, you'll see thin, wispy outliers stretching much farther. And if you measure the humidity profile, the influence of that fog on local air currents might extend even further. Depending on whether you measure light, mass, or reach, you'll call that fog small or enormous. Galaxies are the same kind of puzzle. So, when you hear a number tossed around, 200,000, 500,000, or 1,000,000 light-years, pause and ask what's being measured. Are we talking where the starlight ends, where the gas thins out, or how far the galaxy's gravity can tug on companions? Each answer is valid, and together they give a fuller picture of what big really means in the cosmic sense. To talk about Andromeda, scientists use a unit that already feels unreal: the light year. A light year is simply the distance light travels in 1 year, about 9.5 trillion kilometers. Say it slowly, 9.5 trillion. It's the sort of number that slips out of everyday conversation and into science fiction, and yet it's how astronomers actually measure and compare everything beyond our little neighborhood. Think about the last time you switched on a lamp. The room floods with light, and the change feels instantaneous. That's because light moves so fast, roughly 300,000 kilometers every single second, that even across the width of your room, the travel time is a tiny fraction of a second. If your room is 3 meters across, a beam of light crosses it in about 10 billionths of a second. Our brains register it as immediate, and we rarely think about the messenger doing all the work. Now, stretch that same beam of light across cosmic distances. The nearest star beyond the Sun, Proxima Centauri, is a little over 4 light-years away. When we say a star is 4 light-years away, we mean light. Leaving that star would take more than 4 years to reach us. So even though light arrives here in a heartbeat from a bedside lamp, from the next star over it takes longer than the span of an entire college degree to make the trip. Imagine sending out a message and waiting 4 years for a reply. And that's for the closest stellar neighbor. Andromeda lives on an entirely different scale. When astronomers tell you it's over 2 million light-years away, they're not being poetic. The photons hitting the detectors in our telescopes began their journey before modern human beings existed, long before cities or written language, before agriculture. The light that paints the picture of Andromeda in our telescopes started out on its voyage through the universe, when Earth was a very different place. Looking at the galaxy is, literally, looking back in time, at the state of Andromeda millions of years ago. We use the light year for another reason. It gives us a manageable way to talk about size. Saying a galaxy is 120,000 to 200,000 light-years across sounds weirdly precise compared to giving the same measurement in kilometers. Imagine trying to picture a disk that's 120,000 light-years across in kilometers. The number becomes ungraspable. But 120,000 light-years lets us keep the scale in the same units as the distance. We're measuring everything with the same ruler, the traveler that connects them to us, the beam of light. Why the range in the size 120,000 to 200,000 light-years? Because galaxies don't come with clearly drawn borders. The bright, familiar spiral arms make up the visible disk, where most of the young blue stars and the bulk of the gas and dust sit, and that region is easier to define. Beyond that, things get fuzzy. Older stars drip out into a faint halo. Gas tails and streams from past interactions can stretch farther, and then there's the invisible cocoon of dark matter that dominates the mass and extends even more widely. Depending on whether you measure the bright central disk, the faint extended stars, or the full gravitational halo, you'll get different answers. That's why astronomers are careful to say roughly and give a range. Measuring these things comes back to light, always. To know how far away Andromeda is, astronomers rely on standard candles, objects whose intrinsic brightness we can estimate, like certain variable stars or exploding stars. We compare how bright they appear to us with how bright they truly are, and the difference tells us the distance. To measure its size, we combine that distance with how large it appears on the sky. Angular size times distance equals physical size. Every step uses photons. Light carries the information, and our measurements are only as good as the light that reaches us. That single beam of light is both ruler and clock. It tells us where things are and when the light left them. So when you hear 2 million light years, try to hold two ideas at once: distance and time. It's a distance you could walk for entire lifetimes and still be nowhere near done. It's also a message that departed ages ago. In a sense, Astronomy is a practice of eavesdropping on the universe's past, using the only courier that never tires. Making it personal helps the scale land. Think of 3 milliseconds, the delay on a phone call that feels noticeable. That's like the difference between light crossing your room and light hitting your eye. Now take that tiny, familiar delay and expand it until it's longer than the entire story of humanity. That's what 1,000,000 light years does. It stretches our intuition until familiar units become extraordinary. We can visualize the lamp, the room, the flick of a switch. Then we let the same light slip through space for millions of years. That leap is where awe often sits, between the instantly ordinary and the stupendously ancient. Finally, remember this. Every figure you'll hear about Andromeda, its distance, size, how bright it is, how fast parts of it move, is ultimately a reading of light. Telescopes collect photons, spectrographs split them, and from those streams of information we reconstruct distance, composition, motion, and age. The numbers are built from that single quiet traveler. When you look up at a clear, starry night and see a faint smudge where Andromeda sits, you're looking at a signal that started its journey long before your great-great-grandparents were born. That's humbling, and it's intimate. The universe hands us its history, one beam of light at a time. If you've ever stood under a truly dark sky, no streetlights, no glow on the horizon, just the hush of the night, you might already know this feeling. You look up and notice a faint, ghostly smudge in the north. It's easy to miss if you don't know what you're looking for, and it's easy to dismiss as a cloud or an overexposed star. Hold up your fingertip at arm's length and you'll see what I mean. That soft oval could be covered with a fingertip. It doesn't look like much. And yet that little blur is an entire galaxy, a vast city of stars floating quietly above your head. Why does it look so small? The short version: perspective and sensitivity. Your eye naturally collects the brightest central light of Andromeda, the compact, high-surface brightness core, while the outer swaths, the faint halo, and the diffuse spiral arms are so dim they fade into the background glow of the sky. On a moonlit or light-polluted night, that outer light is swallowed entirely. If your eyes were vastly more sensitive, if they could integrate more photons and ignore the sky glow, Andromeda wouldn't be a speck. It would be an enormous pale disk, several times the width of the full moon, hanging low and gentle over the landscape. Imagine a soft, round wash of light, diffuse at the edges, with a brighter center like a pearl. That's the galaxy you're not usually allowed to see. There's something deeply humbling about that. When I first noticed Andromeda with my unaided eye, I remember thinking how odd it was that something so immense could be reduced to a fingertip-sized blur. Then I trained a pair of binoculars on it, and the scene changed. The oval thickened, the core sharpened, and once you've seen even a hint of structure, your brain starts to fill in the rest. Point a small camera with a long exposure, just a few seconds on a tripod, or better yet, stacked images. And suddenly the full ghostly disk, the outer arms, and the surrounding halo explode into view. The galaxy hasn't changed. We've just given our instruments permission to collect more light than our eyes ever could. If you want to find Andromeda for yourself, the good news is, it's not hard. On clear, moonless nights from mid-northern latitudes, it sits high enough in the sky from late summer through winter. Start with easy landmarks: the Great Square of Pegasus and the bright star Meroc in the constellation Andromeda. From Meroc, follow the line to the next bright star, then keep going about the same distance and you'll hit the fuzzy patch. If you know Cassiopeia's W shape, that's also a great pointer. Andromeda sits roughly between Cassiopeia and Pegasus, leaning north. But don't worry about exact star hopping. Once your eyes adjust to the dark, the smudge becomes obvious. There are a few simple techniques that make the difference between "I think I see it" and "I can't believe I'm seeing this." First, give your eyes time. It takes at least 20 minutes for your rods to reach full sensitivity, and every flashlight or slam of a car door steals that progress. Use a red light if you must read a star chart. Second, use averted vision. The center of your retina is best at sharp detail and color, but the rods that detect faint light are concentrated slightly off-center. If you don't see the smudge when you look directly at the patch of sky, look a little to the side. The faint glow will pop into view. Third, grab binoculars. Even a modest pair, like 7x50 or 10x50, transforms Andromeda. The core becomes compact and bright, and the surrounding fuzz thickens into a clear oval with a subtle gradient. If you want to go beyond binoculars, a wide-field camera or a small telescope will unveil a further truth. Andromeda is not a single, smooth blob. It has structure. Long exposure photographs show a bright central bulge, faint spiral arms, dust lanes, and an extended halo that reaches outward for degrees across the sky. You may even spot the dwarf companion galaxies M32 and M1110 close to the main disk, tiny jewels that orbit the giant. With the right gear, it's easy to forget you're looking at an object outside our Milky Way. From a distance, it reads like a second, slightly more distant galaxy home. There's also a poetic angle worth keeping in mind. When you step outside and really see Andromeda, you're witnessing a kind of cosmic neighbor. Not in a practical visit on the weekend way. It's still 2.5 million light-years away. But as a reminder that our sky hosts more than a single star city. When I point it out to friends and they squint and then grin at the sight, the moment often quiets everything else. Phones put away, conversations pause, and for a few minutes the human-sized worries shrink to the scale of the cosmos. That small smear becomes a bridge, a visible, indisputable proof that there's more out there isn't just an abstract idea in a book. It's a thing you can see without a powerful telescope on a good night. So next time you're out late, away from the city lights, give your eyes a chance. Put your fingertip up to the sky as a measuring stick. Try averted vision. Bring a pair of binoculars. And if you have a camera, take a long exposure. Let yourself look not just at the bright points, but at the faintness between them. That's where the galaxy hides. And when the pale oval finally blooms into sight, take a moment to stand quietly and imagine the countless suns contained within it. A whole separate world of light watching us back from a soft, distant disk. The galaxy hasn't gone anywhere. It's always been there, waiting for us to notice a little more. At the heart of Andromeda's size is its stellar disk, a vast, flat river of stars, gas, and dust that stretches outward like a cosmic pinwheel. Picture it tilted slightly so you can see the sweep of its arms, bright lanes dotted with newborn blue stars, broad swaths of warm red suns, and dark, lace-like ribbons of dust cutting across the glow. Astronomers put that bright, visible disk at roughly 120,000 light-years across, maybe more when you include the faint outskirts, which already makes it larger than the Milky Way by many measures. That number is almost impossible to hold in your head, so it helps to make it personal. If the sun were the size of a beach ball, the entire disk would be a circle hundreds of miles across. Inside that disk, the stars are not scattered randomly. They follow orderly paths. Every star is in motion, orbiting the galactic center the way planets orbit a star. But unlike planets, which follow neat, isolated tracks, stars feel the tug of billions of other objects at once. The gravity that keeps them on those paths isn't just from the visible stars you can see shining at night. It's the combined pull of stars, clouds of gas, dust, and the invisible halo of dark matter enveloping the galaxy. The result is a complex, graceful dance. The inner regions complete their orbits faster, and the outer parts lag behind, which gives the spiral arms their sweeping shape. If you could hover above Andromeda and look straight down, the spiral pattern would be obvious. The arms curve gently outward from the bright central bulge, like fingers unfurling. Along those arms, you'd find places where star formation is happening in real time. Dense molecular clouds collapsing under their own gravity, igniting clusters of hot blue stars that shine like beacons against the darker background. Those bright knots are often wrapped in nebulous gas, glowing H2 regions where ultraviolet light from massive young stars excites hydrogen into a faint pinkish haze. Nearby, lanes of dark dust swallow starlight, forming the dramatic silhouettes so familiar from telescope images. One of the most moving things about a galactic disk is its blend of ages. You can spot the newborns, massive, short-lived blue stars that burn hot and fast, next to ancient, low-mass red stars that have been circling the center for billions of years. That mixture gives the disk a patchwork quality, regions of vibrant youth and quiet seniority, sitting side by side. Star clusters tell a similar story. In the disk, you'll find open clusters, loose gatherings of hundreds to thousands of stars that were born from the same cloud and still travel together for a while before slowly dispersing. Those clusters are like family reunions frozen in space, where siblings born from a single gas cloud keep similar ages and chemical fingerprints. For most of us, when we imagine the size of a galaxy, we picture the disk, that bright, glowing swirl filling our imaginations. It's what telescopes capture most readily, and what dominates the picture postcards of deep space. But to really appreciate it, try thinking about motion and time. A single star near the sun's distance from Andromeda's center takes on the order of a couple 100 million years to complete one orbit. That means the stars we see in the arms now have passed through the same patch of sky countless times over the life of the galaxy. The arms themselves are not rigid highways. They're more like traffic patterns, where stars and gas slow down and bunch together, spark star formation, and then drift on. There's also a physical thinness to the disk that's easy to miss if you only look at pictures. Compared to its enormous diameter, The disk is relatively thin, a few hundred to a few thousand light-years thick in places, which is why we describe it as flat. That flatness gives it a pancake-like elegance, a massive rotating sheet where most of the visible action happens. Because of that, small vertical motions, stars bobbing slightly above and below the midplane, create ripples and waves in the disk over cosmic time, hints that collisions with smaller galaxies or the pull of the halo are constantly reshaping the structure. Even though the disk looks serene from a distance, it's a place of continuous change. New stars are forming from gas that slowly cools and collapses. Older stars expire in supernova explosions that seed the surrounding medium with heavier elements and carve bubbles into the interstellar cloud. These processes recycle material and sculpt the disk's appearance. Dark dust lanes may hide entire regions from optical telescopes, but those dusty regions are often the very nurseries where future stars are waiting to be born. If you've ever looked up at a clear night and felt small standing under the Milky Way's pale band, imagine instead hovering above Andromeda, a river of billions of stars flowing in regular arcs, bright clusters like eddies where the water churns, and threads of dust and gas that give the whole thing texture. That image makes it easier to accept how a galaxy can feel both familiar and utterly alien at the same time. We see the same physical laws at work: gravity, gas dynamics, nuclear fusion, but played out on scales and time so vast they humble our everyday sense of time. This stellar disk, then, is more than just a size measurement. It's the active, visible stage of the galaxy, the place where stars are born, live out their lives, and die, where spiral arms shepherd material, and where the light we associate with Andromeda comes from. It's the part that most people mean when they say, "How big is that galaxy?" But while it dominates our view, the disk doesn't tell the whole story. Beyond and around it lie even more clues: a dense central bulge, faint extended outskirts, and a halo that hides most of the galaxy's mass. And each of those pieces helps explain why the disk behaves the way it does. Moving inward, the galaxy starts to change. The elegant spiral arms and shimmering dust lanes give way to something denser, rounder, and almost claustrophobic in comparison: the bulge. Picture a crowded city center after dark, but instead of buildings and streetlights, there are stars, packed so tightly that the night never really arrives. Near Andromeda's heart, this bulge is a rounded swarm of stars, wrapped tightly around a massive object we think is a supermassive black hole. It's comparatively small on a galactic scale, maybe a few thousand light-years across. But don't let that size fool you. That compact region contains a disproportionately large share of the galaxy's mass. If the galaxy were a family, the bulge would be the stern grandparent who seems small but somehow holds most of the family fortune. Imagine you're standing on a planet inside that bulge. From Earth, we're used to a sky where stars are sparse pinpricks, each separated by wide dark patches. But in the bulge, there would be no wide darkness. The heavens would blaze with thousands of stars so bright they'd outshine anything we're used to. Some would be many times brighter than Sirius. Others would cluster into luminous knots that wash the sky with a soft, constant glow. Night would feel more like dusk, alive, and luminous. This brightness comes from the sheer density of stars. Their orbits are tangled and complex, not the neat circular lanes you picture in the disk. Stars in the bulge follow elongated, plunging, and crossing paths, weaving through a gravitational field dominated by the bulge's combined mass and the pull of the central black hole. Close encounters are common. Stars tug on each other, occasionally scuffing trajectories and exchanging energy. Over millions of years, these interactions shape the structure we observe today. Because of those chaotic orbits, astronomers often describe the bulge differently than the surrounding disk. In fact, it behaves a lot like a tiny elliptical galaxy nested inside the larger spiral. Ellipticals are generally older, redder, and dominated by random stellar motions rather than the orderly rotation of a disk. The bulge mirrors those characteristics. Its stars tend to be older, enriched with the heavier elements from generations of stellar evolution, and their motions are more randomized. Treating the bulge as a separate component helps scientists model Andromeda's mass distribution and history more accurately. There's another reason the bulge draws so much interest: the likely black hole at its center. We can't see the black hole directly, but we can trace its influence. Stars closest to the center whip around at incredible speeds, revealing a gravitational tug that only a very massive, compact object could produce. Watching those tight orbits is like reading the fingerprints of a hidden heavyweight. The motions tell us both the mass of the black hole and hints about how the bulge formed. And speaking of formation, bulges can be born in several ways. Some form long ago when a galaxy experienced rapid, violent bursts of star formation, packing mass into the center. Others arise when the disk itself buckles and reshuffles, funneling gas inward where new stars are born in dense clusters. In Andromeda's case, we see evidence of multiple episodes, a layered history recorded in the ages and chemistry of the stars. Older, metal-poor stars recall the galaxy's ancient youth. Younger, metal-rich populations hint at later gas inflows and star formation. It's like reading tree rings, but on a cosmic scale. The dense environment also makes the bulge a laboratory for exotic astrophysical events. Stellar collisions and mergers happen far more often than in our quiet local neighborhood. Close encounters can trigger sudden outbursts or form unusual stellar systems. And because there are so many stars so close together, the background glow raises the odds of gravitational microlensing events, brief brightenings when one object passes in front of another and magnifies its light. For astronomers, these events are gold mines. They reveal hidden companions, measure masses, and probe the distribution of dark matter in the central regions. From a storytelling perspective, the bulge feels intimate. When we look at Andromeda from a distance, the bulge appears as a bright central knot, a focal point anchoring the galaxy's graceful arms. Up close, that bright knot resolves into an almost claustrophobic neighborhood where life, if it exists there, would be bathed in perpetual celestial light. It's easy to romanticize. Night on a bulge world would be a constant reminder of the galaxy's density and history. A sky crowded with neighbors, each one a story written in light. For the camera, the bulge offers striking contrasts. Wide shots show the spiral structure giving way to a central glow. Zoom-ins reveal a smooth, elliptical brightness rather than the patchy star-forming regions of the disk. Spectroscopic data then adds color to the scene. Redder hues from older stars, subtle absorption lines indicating the chemical fingerprints of past generations. Together, these observations build a portrait of a region that's small in extent, but rich in information. So when astronomers measure Andromeda, they often quote the Bulge separately. It's not just a visual quirk. It's a dynamically distinct component that tells us about mass, formation history, and the physics of dense stellar systems. By studying the Bulge, we learn about how galaxies grow and how massive black holes and stars influence each other in tight quarters. As we leave the Bulge and move back into the disk, carry this image with you: a crowded galactic heart, blazing with stars and memory, a place where the night never quite falls and where the past of the galaxy is written in every orbit. Just past the familiar shimmer of Andromeda's spiral arms, where starlight thins and the colors wash out into a pale haze, the galaxy doesn't end. It spreads. Imagine stepping off a busy coastal highway and walking into a misty marsh that stretches for miles. The lamps of the city are behind you, and ahead there are only scattered beacons and the rustle of long-forgotten currents. That's the stellar halo, a vast, faint, ghost-like region made of lone stars, compact globular clusters, and the thin, ribbon-like streams of stars that were torn from smaller galaxies and woven into Andromeda's outskirts long ago. If the bright disk is the city center, the halo is its hinterland. It's not a tidy suburb with neat rows of houses. Instead, it's a sparsely populated countryside where most of the land is empty and the occasional homestead, a globular cluster or a star stream, sits isolated for thousands of light years. The density of stars out there is so low that you could travel distances that would normally take centuries at light speed without passing close to another sun. Picture the night sky on one of the darkest, most remote stretches of Earth. The stars seem infinite, but the gaps between them are enormous. That's the scale we're talking about. How far does this reach go? The halo stretches well beyond the visible spiral, perhaps 3 to 5 times farther than the bright disk. And some studies suggest it extends out to several 100,000 light-years from Andromeda's center. To put that in human terms, the bright disk is already tens of thousands of light-years across. The halo pushes the galaxy's influence far into the surrounding intergalactic space, approaching regions that are cosmically closer to our own Milky Way than to Andromeda's luminous core. In other words, Andromeda's presence is felt across a truly vast arena of space. The stars that inhabit the halo are typically old and chemically poor compared to those in the spiral arms. They are like elders keeping memory of the galaxy's past, ancient, slightly weathered by time, but rich in the story they carry. Many are red giants or other late-life stars that shine brightly enough for us to spot them individually, but most are faint pinpricks that only sensitive telescopes can resolve. Their metallicity, the amount of elements heavier than helium, is low because they formed early in the universe's history, before multiple generations of star formation had pumped heavy elements into their surroundings. When you look at these stars, you're looking at fossils of the galaxy's formative years. Scattered within that haze are globular clusters, dense, spherical collections of hundreds of thousands of stars packed into regions perhaps 100 light-years across. These clusters are like ancient citadels standing in the fog. From a human perspective, they would act as familiar landmarks, obvious, compact spotlights in an otherwise dim landscape. Some of Andromeda's globulars are as old as the galaxy itself, and hold clues about conditions in the early universe. They are useful for astronomers because their motions and compositions tell a story about how the halo assembled over billions of years. Even more telling are the star streams, long, slender trails of stars that arc away from the galaxy like tattered ribbons. Those streams are the smoking guns of galactic cannibalism. Over cosmic time, Andromeda has grown by swallowing smaller dwarf galaxies. As these dwarfs came too close, tidal forces stretched them apart, leaving their stars strewn along their orbital paths. If you could fly along one of these streams, you'd be following the remnants of a vanished galaxy. Its core dispersed, its identity dissolved into the halo. Observationally, these streams are faint but distinct when you count individual stars and trace coherent motions. They act like archaeological layers. Each one can often be traced back to a specific accretion event and dated to reconstruct Andromeda's merger history. Detecting and mapping the halo isn't easy. The surface brightness is extremely low, which means that imaging it is like trying to photograph fog under a full moon from a moving car. Astronomers use star counts and deep integrations with powerful telescopes, plus surveys that stitch together thousands of images to reveal its structure. Projects like the Pan-Andromeda Archaeological Survey, PANDAS, have peeled back the veil, showing a complex lopsided halo with substructures, overdensities, and streams that betray a violent past. Hubble and ground-based giants like Subaru and Keck have been essential to resolving individual halo stars and measuring their motions and chemical fingerprints. Why should we care about this diffuse, lonely region? Because the halo is the memory bank of a galaxy. The bright disk shows us the present, where new stars are forming, where gas swirls in arms, where spiral structure organizes the light. The halo, by contrast, is a ledger of everything that happened to build that present. Every small galaxy tugged on, every collision, every piece of material accreted. Reading the halo is how astronomers reconstruct the sequence of mergers that shaped Andromeda into the galaxy we see today. It's also where the galaxy's gravitational influence extends farthest. The orbits of halo stars and clusters feel the pull of Andromeda's dark matter halo. Even though the halo is diffuse and faint, it marks the true boundary of Andromeda's domain. There's also a very human layer to this story. When you imagine standing on a platform at the edge of the Milky Way and looking across the gulf to Andromeda's halo, there's something profoundly intimate and humbling about it. These faint stars are lonely in a way that makes ours feel more precious. Right now, most of us live under a sky dominated by the closer, brighter sun and its companions. But out there, in those remote reaches, solitude is the rule. A star might not have a neighboring sun within light years. Yet those isolated stars are not irrelevant. They are witnesses. Each one has traveled an ancient path, part of a stream, clinging to the halo like an old photograph pinned to a weathered wall. And there's a dynamic future in that ghostly quiet. Andromeda and the Milky Way are on a slow-motion collision course. Over the next several billion years, the halos of the two galaxies will interact and interpenetrate long before the cores meet, and those faint outskirts will be the first to feel the gravitational tug of that encounter. Streams will be distorted further, clusters will be thrown into new orbits, and the combined gravitation of the two massive halos will rearrange the structure of both galaxies. In a sense, The halo is the first handshake between Andromeda and us. So when we talk about galactic boundaries, don't think of a crisp edge. Think instead of a long tail of scattering light and sparse residents that extend far beyond the parts we usually admire. The halo is quieter, older, and much more revealing than its paler appearance suggests. It's the archive of collisions, the map of past encounters, and the measure of gravitational reach. If you want to understand Andromeda, not just as a beautiful spiral, but as a living system with a history, you have to step out into that faint outer region and read the ghostly traces written there. Even the halo is not the full story. Andromeda, like our own Milky Way, wears a bright, flat disk of stars that you can photograph on a clear night. But wrapped around that disk is something far bigger and completely invisible, a halo of dark matter. It doesn't shine. It doesn't absorb light. And yet, because it has mass, it has gravity. And that gravity sculpts how everything inside and around the galaxy moves. Think of it this way. If the visible stars and gas were the furniture in a house, dark matter would be the foundation and framing hidden behind the walls. You don't see it, but without it the whole structure would sag and collapse. Astronomers realized this decades ago by watching the way stars and clouds of gas orbit the galactic center. If only the luminous matter were holding things together, those outer stars should be drifting away, moving more slowly as distance increases. But they don't. Instead, their speeds stay surprisingly high. It's as if someone attached an invisible weight to the galaxy, keeping the outskirts pinned in place. That observation, the flat rotation curve, was one of the clearest signs that there's more mass than we can count with telescopes. Vera Rubin and others measured those motions in the 1970s and helped turn a shadowy anomaly into a major piece of the cosmic puzzle. Since then, multiple lines of evidence have reinforced the conclusion. The motions of satellite galaxies, the temperature and distribution of hot gas, and even the way light from background objects is subtly bent by gravity, gravitational lensing, all point to a massive unseen envelope surrounding galaxies. How big is this envelope around Andromeda? Models suggest it could stretch 1 million light-years or more from end to end. To put that in perspective, Andromeda's luminous disk is a few 100,000 light-years across. Impressive on its own, but the dark halo is a whole different scale. If you could step outside the galaxy and measure the invisible boundary, you'd find that it likely reaches far beyond the bright stars, a diffuse, ghostly sphere extending into intergalactic space. Here's a more down-to-earth analogy. Imagine two houses separated by a city block. Their porches and yards are obvious, but imagine if both houses also had enormous, transparent domes extending over many blocks. From the outside, you'd only see the houses. The domes would be invisible, but those domes would overlap far sooner than the houses' porches ever would. That's essentially what's happening with Andromeda and the Milky Way. Their visible disks are distant neighbors, but their dark matter domes may already be brushing against one another. That overlap changes how we think about the local group. It means Andromeda and the Milky Way aren't isolated islands floating independently. They're already tugging on each other through this shared invisible medium. In practical terms, that gravitational tug helps set the future of our cosmic neighborhood. It influences orbital paths of satellite galaxies, alters how gas flows between the two giants, and factors into the timing and dynamics of the eventual collision that will reshape both systems billions of years from now. Of course, dark matter is a placeholder name. We know it by what it does, not by what it is. Countless experiments and telescopes try to catch a glimpse of it in the lab or through its other effects. But so far the particles themselves, if that's what they are, remain elusive. The leading idea is that dark matter is made of some kind of weakly interacting particle that barely feels electromagnetism, so it doesn't light up or clump like ordinary matter. It behaves mostly like a gravitational glue, heavy enough to pull things together, but ghostly enough to remain undetected by light. Inside that halo, though, dark matter isn't perfectly smooth. Simulations of cosmic structure and observations of satellite galaxies suggest it's lumpy, dotted with smaller subhalos, the skeletons where dwarf galaxies can form or fail to form. Imagine the halo as a fog with thicker and thinner patches. Some of those denser clumps host tiny companions that orbit Andromeda. Others might be dark entirely, never gathering enough normal matter to light up with stars. Those substructures are important because they leave fingerprints in the motions of stars and gas, and they help astronomers refine models of dark matter's properties. It's worth saying how much of Andromeda's mass is hidden this way. Estimates suggest that the dark halo outweighs the visible parts by a wide margin, often by factors of 10 or more. So when we say how big is Andromeda, there's a two-part answer. One for the dazzling star-filled disk you can see in a photograph, and a much larger, more mysterious one for the invisible halo that dominates the galaxy's mass budget. That difference changes the way we relate to the universe. Standing under the night sky, you might feel like an individual living on a bright, well-lit street. But on cosmic scales, your street is nested inside a vast, unseen neighborhood, an envelope of gravity that links you to distant galaxies. The idea that our galaxy and Andromeda may already share overlapping dark matter halos is oddly intimate. It means, in a very real gravitational sense, we're not just neighbors in name, we're connected. And that connection has consequences. When scientists simulate the future collision between Andromeda and the Milky Way, they don't just model two disks slamming together. They model two enormous, dark halos, first meeting and merging, their gravitational interplay steering stars and gas long before the visible galaxies touch. The halos act like cosmic choreographers, guiding the dance that will eventually assemble a single larger system. There are still big unknowns. How exactly dark matter is distributed at the very outskirts, whether halos are spherical or stretched into elongated shapes, and how much the two galaxies' halos already overlap. New surveys, deeper observations of faint satellite motions, and improved maps of gravitational lensing are slowly tightening those uncertainties. Each piece of data is like feeling the contours of that invisible dome with a blindfold on. You can't see it, but you can map its edges by how it moves the things inside it. So when someone asks how big Andromeda really is, you can give a simple answer: the glittering disk you can photograph, and then a more humbling one. It's embedded in a vast invisible envelope that stretches much farther, perhaps 1,000,000 light-years across, and may already be touching ours. That invisible envelope is the reason Andromeda behaves the way it does, the stage upon which future encounters are set, and one of the biggest reminders that much of the universe's mass is written in darkness we've yet to fully understand. Next, let's look at how that dark envelope affects the fainter companions around Andromeda, the dwarf galaxies and star streams that trace the halo's shape and give us more clues about its hidden architecture. So is Andromeda actually bigger than the Milky Way? Short answer, yes, most of the time, by the measures astronomers usually use. Longer answer, it depends on what you mean by bigger. Let's walk through the ways we compare galaxies, what the numbers tell us, and why the comparison always has a little wiggle room. First, think about shape. When astronomers talk about a galaxy's disk, they mean the flat, spinning plane where most of the visible stars live. Andromeda's disk looks noticeably wider than the Milky Way's bright disk. If you could step far away and put the two galaxies next to each other, Andromeda would be the one that spreads out more, a broader, more luminous sweep of stars and gas. Its central bulge, that dense, rounded concentration of older stars around the center, is also chunkier. In simple visual terms, Andromeda has a bigger torso and a more prominent belly. Now for the star count and the idea of stellar mass. When researchers estimate how many stars a galaxy contains, they usually convert light into mass, measure how much light is coming from the galaxy, correct for stellar populations, and infer how many suns worth of mass that light represents. By that yardstick, many studies land on the same headline. Andromeda likely has something like 1.5 times as much mass in stars as the Milky Way. If you imagine our galaxy as a house with, say, 5 rooms full of furniture, Andromeda might have 8. That doesn't mean every piece of furniture is identical, only that there's more of it overall. But there's a catch. Counting from the inside is messy. We live inside the Milky Way, which is at once a convenience and a nuisance. It's like trying to map your own home while crawling under the furniture. You can see a lot of detail up close, but you miss the shape of the whole room. Dust lanes, spiral arms, and overlapping structures hide parts of the galaxy from our direct view. And because we're embedded in it, surveying the outer regions or faint components requires clever tricks and indirect measurements, and those carry uncertainties. Contrast that with Andromeda. We get to see it as an external observer. From Earth, we can take a single frame and study its overall contours, where the light falls off, how the arms wind, how the bulge sits against the disk. That outside perspective makes it easier to gauge global properties like disk width and brightness profiles. So, paradoxically, even though Andromeda is a neighbor 2.5 million light-years away, in some ways we've mapped its overall shape more cleanly than we've mapped our own. Another crucial distinction is between stellar mass and total mass. Stellar mass is the mass locked up in stars. Total mass includes stars plus gas, dust, and the invisible dark matter halo that dominates a galaxy's mass budget. Many of the statements about Andromeda being bigger refer specifically to stellar mass. When it comes to total mass, especially the dark matter halos, the picture gets foggier. Some measurements suggest the Milky Way's total mass could be comparable to or even larger than Andromeda's, depending on how you weigh the halo and which observational tracers you trust. So on the "how much gravity is sitting there" question, the answer isn't settled. There's also surface brightness and apparent intensity. Because Andromeda's disk and bulge are more populated, it tends to appear a bit brighter per unit area, when you look at the regions that host the bulk of the stars. That brightness contributes to the impression you get if someone handed you two photos. The Andromeda picture would look slightly more luminous, a little fuller. It's not an enormous difference, more like one sibling who keeps the living room a bit tidier and so always looks a touch more presentable at gatherings. Why does any of this matter beyond trivia? For one thing, it shapes how the two galaxies will evolve and interact. A more massive bulge may indicate a different merger history. A wider disk speaks to how gas settled and formed stars over billions of years. Those differences influence the dynamics of the future collision between the two systems and the kinds of star formation fireworks we might, in theory, expect. They also help us place both galaxies in the broader context of how galaxies grow. Mergers, gas inflows, and internal processes all leave fingerprints in disk size, bulge prominence, and stellar mass. On the personal side, this comparison is one of those cosmic stories that makes the universe feel like a neighborhood. When we look out into the sky and see the faint smear of Andromeda on the rare, truly dark nights, it's tempting to picture a quiet, distant city of stars. Knowing that it's probably just a little larger than our own galactic home gives the encounter a human scale. It's like noticing your neighbor's house has a slightly wider porch and a brighter porch light. Familiar and comforting, but just a touch grander. It's also a reminder of perspective. If you stand inside a forest, the nearest trees can block your view of the clearing. Standing outside the forest, you see the pattern of trees and the shape of everything around it. We have the insider's intimacy with the Milky Way and the outsider's overview for Andromeda. And both points of view are valuable and imperfect in their own ways. So put them side by side in your mind. Andromeda would be the slightly bigger sibling, a little wider across the hips, a fuller central bulge, a touch brighter when you glance over the cosmic fence. Not astronomically larger in the sense of being orders of magnitude different, just noticeably more massive in stars and visually more expansive. It's the kind of neighbor who, when you step outside and glance up, you can't help but notice, familiar enough to feel close, different enough to be interesting. Picture a quiet, clear night where you can see the galaxy as a bright smear over the horizon. Only now that smear belongs to Andromeda, not the Milky Way. For this thought experiment, we swap the two galaxies as gently as possible, keeping the sun exactly where it is. Everything local to us stays put. The difference is the landscape of stars sprawled above. On nights when the sky is truly dark, Andromeda's disk would be impossible to miss. Instead of the thinner, mottled band we call the Milky Way, you'd see a broader, more luminous ribbon of light. It would stretch farther and look thicker, like someone took the familiar river of stars and poured a little more starlight into it. The overall effect would be like upgrading from a dim string of fairy lights to a more elaborate, brighter festival display. Still subtle, still beautiful, but undeniably more dramatic. Walk outside and lie on your back the way you might have on summer camping trips. The individual stars closest to us would still appear as points of light, but between them you'd notice clumps and knots, compact clusters, and the soft, rosy glow of star-forming regions along the spiral arms. Those nebulae, where new stars are igniting, would add splashes of color, pinkish hydrogen clouds, blue-white nurseries of young hot stars, and darker lanes of interstellar dust threading across the brightness. It wouldn't be a single solid glow. You'd be able to trace the spiral pattern if your eyes and the conditions were good enough. For someone who grew up under the familiar Milky Way, that pattern would feel like seeing an old city from a different hill, a familiar geometry, but with new neighborhoods to explore. What would that do to how you experience the night? For starters, the sky would feel richer. Subtle features that are usually washed out might pop into view. Faint clusters that hide in our galaxy's glare could stand out against Andromeda's broader backdrop, and some emission nebulae would look more prominent. Photographers and amateur astronomers would have a field day. The long exposure shots would show swirling arms and bright knots, and backyard telescopes would pick out new contrasts. But it wouldn't turn night into day. The diffuse light would be brighter than what we're used to in very dark places, but the difference is not enough to change our daily lives. Streetlights, indoor lamps, and the sun would remain the real determinants of visibility. Life here on Earth would go on almost entirely as it does now. Your morning alarm and your coffee routine would be unchanged. Earth's climate, seasons, tides, and the mechanics of the solar system would be unaffected by swapping the distant galactic halo around us. The sun would keep carrying us around whatever galactic center we now call home, taking the same slow, majestic orbit that spans hundreds of millions of years. Those enormous timescales, your lifetime is a blink, remind us that galaxies are the stage on which our story unfolds, not the director of our everyday script. It's tempting to imagine that a bigger galaxy means more danger, close stellar passes, increased supernova threats, or a higher chance of catastrophic encounters. But the key thing to remember is scale. Even a slightly larger spiral is vast beyond comprehension, and its stars are spaced so widely that any given star is mostly alone. The empty stretches between suns don't shrink enough to make collisions likely on human timescales. From our point of view on Earth, the neighborhood remains sparse. The dramatic structures we see in Andromeda, glowing knots of newborn stars, dense spiral arms, are impressive because they're huge, not because they bring stars closer to us. Emotionally, though, the swap would shift something about how we feel under the sky. There's a strange comfort in familiarity. Those smoky lanes of the Milky Way are part of our cultural memory. Replace them with Andromeda's broader ribbon, and you'd still feel the same smallness, but with a different flavor, more vivid, more active, a little less solitary in its appearance. The galaxy would look busier, as if more things are going on at once. That visual busyness could alter the tone of stargazing moments. Nights that once felt solemn might now feel electric, and the sense of being a single point in a vast quiet might tilt toward feeling like you're a window seat looking into a bustling metropolis far in the distance. And yet that shift is psychological more than physical. The laws of gravity, nuclear fusion in the sun, plate tectonics, none of them would suddenly behave differently. Our immediate cosmic risk doesn't spike. We wouldn't suddenly be peppered by more comets or find a neighboring star drifting dangerously close. The distances that protect us would remain enormous. There's a poetic lesson tucked into this thought experiment. On one level, it's a demonstration of scale. Andromeda is bigger, brighter, more ornate, and yet from any single world in its disk, the experience is delicately similar to ours. Lonely, expansive, and quietly magnificent. Galaxies are like grand, diffuse artworks hung far above us. You can stand beneath a larger painting and appreciate the extra detail, but the canvas is still painted from a distance. Our sense of solitude under the stars doesn't stem from a lack of objects in the sky, so much as from the hugeness of the spaces between them. So imagine lying back and tracing those spiral arms with your mind. Think about how the pinks and blues of star formation would catch your eye, how clusters might pepper the band like city lights, and how the whole spectacle would feel just a touch louder than what you remember. It would be a richer backdrop for the same human dramas: birth, love, routine, and curiosity played out on the small stage of Earth. The galaxy around us could be swapped for a slightly larger, more luminous neighbor, and life would remain stubbornly ordinary and quietly extraordinary at the same time. Another way to think about a galaxy's size is to ask how many stars it holds. Picture that question for a moment. Not how wide it is in light years, but how many suns are packed into that swirl of light. For Andromeda, the answer we usually hear is about 1 trillion stars, maybe more. For the Milky Way, the common estimates are a few hundred billion. Those are staggering numbers, but they aren't carved in stone. Astronomers don't go out with a giant cosmic tally. They infer these totals from the light a galaxy gives off, and from models that predict how many small, dim stars must be hiding in the glow. So how does that inference work, without individually counting each pinprick of light? Think of a city photographed from space at night. Bright downtowns tell you where most of the population lives, but a million tiny backyard lights don't show up as clearly. To estimate the total population, you'd combine the visible lights with statistical models about how many households you expect per block. In astrophysics, light is our map. We measure the galaxy's total brightness across different wavelengths: visible, infrared, ultraviolet, and use stellar population models and a concept called the mass-to-light ratio to convert that brightness into a likely number of stars. There's an important twist. Not all stars are created equal. A single massive star can outshine 100 small red dwarfs, so brightness alone can be misleading. That's where the initial mass function, often shortened to IMF, comes in. It's a statistical rule that tells us how many stars of each mass form in a typical stellar population. Combine that with our observations of a galaxy's overall light, and you can infer how many faint, numerous, low-mass stars must be present, even though they contribute little to the total glow. In other words, the galaxy's light gives us the loudest voices. The IMF helps us estimate the quiet crowd in the background. We also take advantage of resolved star counts where possible. The Milky Way is close enough that we can tally individual stars in many directions, and in nearby galaxies like parts of Andromeda, we can resolve individual bright giants with powerful telescopes. Those direct counts anchor the models. For more distant systems, we rely on integrated light combined with what we've learned locally. Infrared observations help too. Cooler, red dwarf stars and dust-obscured regions reveal themselves better at longer wavelengths. Even with all those tools, there's room for uncertainty. Dust can hide light. Older stars have different spectra than younger ones, and the exact shape of the IMF might vary from one galaxy to another. That uncertainty is why astronomers give ranges: a few hundred billion for the Milky Way, 1 trillion or more for Andromeda, instead of a single neat number. But the broad picture is clear. Andromeda likely contains several times as many stars as our galaxy. It's not a minor difference. It's like comparing a sprawling metropolis to a very large city. Those raw numbers can be hard to feel, so let's bring them into a human scale. If each star in Andromeda were a single grain of sand, the galaxy would be a mountain, an impossible heap across the night sky. If each star were 1 second of time, counting them at 1 per second without pause would take around 30,000 years just to finish Andromeda's population, and that's if the total is only 1 trillion. Even the Milky Way's few hundred billion seconds stretches past anything in our lifetimes. The metaphors aren't meant to make us feel small in a depressing way. They're meant to shift perspective. Our sun and our planet are intimately familiar, life-changingly important to us. And yet, they're a single address in one neighborhood of an enormous cosmic city. It's also worth pausing on what counting the stars tells us beyond vanity. The number and types of stars in a galaxy speak to its history. How fast it formed new stars in the past, how many mergers and collisions it experienced, and how much material it has left for future star formation. A galaxy teeming with massive blue stars must have been forming stars recently. One dominated by dim red stars suggests an aging population. Knowing the stellar census lets astronomers estimate the galaxy's stellar mass, compare it to the mass of dark matter inferred from rotation curves and motions, and piece together its evolutionary story. On a personal note, I remember lying on my back in a small town, counting Orion's bright pattern, and thinking that each speck was a star like ours. There was something profoundly intimate and liberating about that, realizing that the same basic physics that makes our sun burn also lights those distant points. When you learn that a single neighboring galaxy could host numbers of stars beyond comprehension, that intimacy doesn't vanish. Instead, it deepens. Our sun becomes not a lonely lighthouse, but one family member in a vast ancestral tree of stars that spans galaxies. Finally, that neighborhood metaphor is useful. The Milky Way and Andromeda are neighbors in a local group of galaxies, each with its own population and history. Knowing how many stars they contain helps us understand how common planetary systems might be, how often galaxies collide, and what the future may hold for our corner of the universe. So when you next look up and see the Milky Way band across the sky, try to imagine it not just as a blur of stars, but as a dense community, a place with hundreds of billions of lives and potential stories. It doesn't make our own story any less precious. It makes it part of a much larger, richer tapestry. Andromeda does not drift through space alone. Around it swarm dozens of smaller companion galaxies, many of them faint and irregular in shape. If you picture Andromeda as a bright city skyline at night, its satellites are like the dim suburbs and cottages that cling to the outskirts, some neat and compact, others spread out and hard to make out until you really squint. They aren't just decoration. These companions trace the invisible contours of Andromeda's gravity and tell a history written over billions of years. Imagine the galaxy surrounded by an enormous unseen atmosphere. That's the dark matter halo. It doesn't glow, but it reaches far beyond the shiny spiral we see in images. Within this halo, the smaller galaxies orbit, circling the giant like moons circling a planet. The analogy helps. The satellites move under Andromeda's gravitational pull, trapped in its potential well. Their orbits, speeds, and positions give astronomers the clues they need to measure how much mass, visible and invisible, Andromeda really contains. Some of these companions are tiny, compact objects that sit close to the main disk like bright knots. Two of the most famous are M32 and M1110. To a backyard telescope, they look like small extra pieces glued to the larger picture, but up close they're whole galaxies in miniature, each with its own stars and structure. Then there are dozens of fainter dwarfs, irregular in shape, often containing only a few million to a few billion stars, a tiny fraction of the hundreds of billions in Andromeda itself. Many were discovered only recently with deep surveys because they're so faint. They're whisper-quiet members of the family, easy to miss until someone points them out. Not all companions are peaceful or immutable. Gravity is a storyteller that sometimes tells tales of violence. As these satellites orbit, Andromeda's tidal forces can stretch them apart. Picture a small clump of stars falling too close to a galactic giant. The side nearer to Andromeda feels a stronger pull than the far side, and over time, that difference pulls the dwarf galaxy into elongated streams. The most dramatic example in our neighbor is the giant stellar stream, a great ribbon of stars arcing through Andromeda's halo, the remnant of a galaxy long ago disrupted and assimilated. Those stretched out stars wrap around the disk like tattered banners, evidence that galactic cannibalism has been part of Andromeda's growth. These tidal streams are beautiful for more than aesthetic reasons. They're forensic evidence. By mapping where the streams lie and how the stars move within them, astronomers can rewind the interactions and estimate when a satellite was torn apart, how massive it once was, and how the dark matter halo is distributed. It's like looking at tire tracks in the snow and reconstructing the path of a car. The tracks tell you about the vehicle's weight, speed, and direction. Here, the tracks are made of stars. Not every satellite gets shredded. Some remain compact, holding together like stubborn beads on a string. Others orbit far out, barely feeling the tug of Andromeda's inner regions. When astronomers talk about the Andromeda system, they don't mean just the bright spiral we see in photographs. They mean that spiral plus all these companions, streams, and the diffuse halo around them. Count the satellites out to the furthest ones still bound gravitationally, and the whole structure stretches well over 1 million light-years from edge to edge. To put that in perspective, our own Milky Way and Andromeda are about 2.5 million light-years apart, and yet each of them extends a huge halo-like reach filled with companions and debris. There's a human side to this cosmic neighborhood. Think of a family portrait. The parents in the center, kids bustling around, grandparents on the edges. Some are tidy, some are ragged. Some have long since moved away but still leave traces. The satellites are Andromeda's relatives, some living quietly, some recently arrived, some long since torn to pieces, yet still visible as ghostly relics. For astronomers, each member is a character in a long-running drama. Where did it come from? When did it join the family? How will it change the whole system over time? Observationally, detecting these faint companions is a mix of patient surveying and clever techniques. Deep imaging catches faint smudges of starlight. Star-by-star mapping reveals sparsely populated dwarfs. Spectroscopy measures velocities to confirm whether a fuzzy object is really orbiting Andromeda or just a background galaxy much farther away. Over the past 2 decades, surveys have multiplied the census of Andromeda's satellites, and with each new discovery, the picture of the system becomes richer and more complex. What once looked like a solitary spiral now reads more like a bustling metropolis with an extended commuter belt. And the satellites are not just tracers of past events, they're active participants in the galaxy's future. As they spiral inward, perhaps losing energy through dynamical friction, some will eventually merge completely with Andromeda, contributing their stars to the disk, halo, or bulge. Those mergers can spark bursts of star formation, rearrange stellar orbits, and subtly reshape the galaxy's structure. In that sense, Andromeda's size and identity are not fixed by the shine of its spiral arms alone. They're defined by an entire family that moves with it, sometimes tugging, sometimes surrendering, always influencing the whole. So when you look at an image of Andromeda, try to widen your mental frame. Don't just see the bright spiral. Imagine the faint, ghostly companions tracing out long orbits, ribbon-like streams wrapping around the halo, and compact knots holding their ground. The galaxy's true scale is its social network. The satellites, the streams, the halo that binds them. That web of relationships is what makes Andromeda not just a single object in space, but an entire system with history, dynamics, and a future that stretches across more than 1 million light years. Think about that. The faint smudge of light you can spot on a clear night began its journey toward your eyes about 2.5 million years ago. That beam left Andromeda when our very distant relatives, early human ancestors, were just learning to chip stone and make the first simple tools. So when you look up, you're not just looking across space, you're looking back in time. The light is a message in a bottle from an era before cities, before agriculture, before language as we know it. That fact changes how we imagine the size of Andromeda. It's not enough to say it's big. You can picture its spiral arms and its glowing center, but those are tiny details compared to the emptiness between us. The galaxy itself is enormous, yes. Hundreds of billions of stars arranged into a disk, hundreds of thousands of light years across. But the gulf separating its disk from ours is vaster still. If you tried to fill that gap with Milky Way-sized disks laid edge to edge, you could fit many of them into the void and still have room to spare. Imagine a chain of huge, glittering islands scattered across an ocean so wide you'd need more than a lifetime of sailing to cross it. And yet that ocean is not empty in the way we usually think of emptiness. Gravity reaches across that gulf. It's subtle and patient, not like wind pushing a ship, but constant. The Andromeda Galaxy and the Milky Way are locked in a slow, mutual tug. Right now, they're drifting toward each other at a speed measured in hundreds of kilometers per second. That number sounds absurdly large, and it is. To put it into a frame you can feel, a few hundred kilometers per second is faster than any rocket we've launched, faster than a speeding bullet by orders of magnitude. Still, on intergalactic scales, it's a gentle crawl. That approach happens not because either galaxy is plowing through some cosmic medium or because someone flipped a switch. There's no air or water in intergalactic space to slow or steer them. Instead, their mutual gravitational attraction, the invisible pull every mass exerts on every other, slightly alters each galaxy's path. Imagine two dancers on an enormous, frictionless floor. Each dancer's steps are shaped by the other's presence. Neither is being pushed from behind, but the way they move curves toward one another. Over billions of years, Those tiny nudges add up. The distance between them slowly decreases until their edges begin to meet. That timescale is almost impossible to grasp in the moment-to-moment rhythms of human life. We measure our lives in decades, our family histories in centuries, a civilization in millennia. The shrinking of the space between the Milky Way and Andromeda plays out across millions and billions of years, a slow-motion choreography that would barely register across a single human lifetime. If the light you see now left Andromeda when our ancestors were first using stone tools, the eventual collision will occur long after our civilization as we know it has evolved into something else. Still, the idea has a personal edge. Think about how we relate to neighbors in our own lives. Sometimes we live on streets where properties are a few meters apart. Sometimes there are yards and fences. Sometimes entire parks, separate houses. Now scale that up until the fence is a vacuum and the yard is 2.5 million light years across. Even then, the neighbors feel each other. The pull is real. That cosmic neighborliness is comforting and a little unnerving at the same time. It reminds us that even in the vastness, connections persist. There's also a gentle poetry to the fact that the starlight reaching your eyes tonight is like a story told by a time traveler. When you find Andromeda on a dark night, you're seeing it as it was when the first toolmakers scratched flint on stone. If you could somehow step into a spacecraft and fly there instantly, you wouldn't arrive at the Andromeda you see in the sky. You would meet its present, not its message. Conversely, any photograph we take of Andromeda is a photograph of the past. Every pixel is a tiny historical record. Visually, this is a powerful idea for a video. Show an animation of light leaving Andromeda 2.5 million years ago, a single photon embarking across the black, and then cut to early human hands crafting tools. Follow that photon as our distant past folds into the present. Overlay that with a graphic of the two galaxies set, like massive clock hands, slowly swinging toward one another. Keep the music slow and inevitable. There's no rush here, only the steady inevitability of gravity. One last thing to carry forward. Distance here is not merely about separation, but about relationship. The emptiness between us emphasizes the scale, but it also makes the pull more dramatic. Two giants drifting together over unfathomable distances reminds us how unhurried and persistent the universe can be. It's a cosmic slow dance where time is the choreographer and gravity the music. So, with that gulf and that slow, inexorable pull in mind, what happens when the dance speeds up and those two spirals finally meet? Let's move on and find out. From a distance, it will look almost choreographed. Two great luminous spirals closing in, their bright discs beginning to overlap, arms stretching into graceful, violent ribbons. For a while, the sky would be dominated by a second galaxy, a slow, magnificent intruder, its pale starlight washing across our night. Those arms will twist and coil under the tug of gravity. Tidal tails will snatch stars and gas, slinging them into long, comet-like streams that glow for millions of years. But it's crucial to step away from the Hollywood idea of a smash-up. Galaxies don't collide like billiard balls. They're mostly emptiness. Even in a dense stellar environment, the average distance between stars is huge compared to their sizes. So when we say Andromeda and the Milky Way will collide, we mean their structures will interpenetrate, and their gravitational fields will remix, not that individual suns will routinely smash into one another. If you could sit on Earth and watch, very likely you wouldn't see another star physically hit the sun. Instead, you'd watch the whole stellar ensemble change its dance. What actually meets and merges are the invisible and the diffuse, the dark matter halos that dominate both galaxies' mass, the vast and tenuous clouds of hydrogen and helium, and the orbits that define where stars live. Dark matter is the hidden scaffolding. It extends far beyond the bright disks, and when those halos overlap, they reshape the gravitational landscape. Stars that once circled peacefully in ordered, flat disks will find their orbits torqued into more chaotic patterns. The ordered rotation that makes a spiral look the way it does will slowly be randomized. Gas behaves differently than stars. When the Milky Way's and Andromeda's cold gas clouds meet, they can collide and compress. Those collisions are the true fireworks. Compressed gas ignites new generations of stars, often in intense, short-lived bursts. So the merger won't be just a matter of empty orbits rearranging. It will also be a time of rebirth. Pockets of brilliant blue-white newborn stars will flare across the sky, sometimes hidden behind curtains of dust, sometimes shining like cosmic fireworks. If you care about star formation, this is the moment. Gas clouds collide, collapse, and light up the darkness. There will also be dramatic encounters near the centers. Each galaxy harbors a supermassive black hole. When the two galaxies finally coalesce, those black holes will spiral toward each other in the dense central regions and eventually merge. That final embrace could light up the core as an active galactic nucleus for a time, pouring energy into the surrounding gas and possibly blowing some of it away. The black hole merger itself would send ripples through space-time, gravitational waves on a scale we can't feel, but instruments far in the future might detect. Timescales are important to keep in mind because collision feels urgent, but the process is glacial. Andromeda is currently about 2.5 million light-years away and closing at roughly 100 kilometers per second. The first close passage is predicted in roughly 4 billion years, and the settling into a single new galaxy will take several billion years more. That's long compared to a human lifetime, but short on the cosmic calendar. Over those eons, the galaxies will weave through each other several times. Each pass shreds the disks further, steals gas, and alters orbits. Eventually, the spiral patterns dissipate, and the merger remnant relaxes into something more spheroidal. Many simulations show a giant elliptical galaxy as the likely outcome, though details depend on how much gas is left and how the interactions play out. So, what does this mean for our sun and the planets we call home? The honest answer is uncertain, but not apocalyptic in the way movies suggest. The probability of a direct hit between stars is vanishingly small. Think of the galaxies as clouds whose individual droplets mostly miss. However, the gravitational reshuffling can nudge the solar system's orbit around the galactic center. Over time, these nudges could displace us. We might be thrown out toward the galaxy's outskirts, or shepherded closer to the new core. Either way, the sun's environment would change. It might get a quieter sky if we end up in a sparsely populated halo, or a busier one if we're tossed into dense stellar streams. There's a wrinkle, though: the sun's own life clock. In about 5 billion years, the sun will exhaust the hydrogen in its core and expand into a red giant, an event that has more immediate implications for Earth's habitability than a galaxy collision. So whether Earth, or something like it, survives as a cradle for life through a galactic merger is as much a question of stellar evolution as it is of dynamics. If humanity or its descendants are still around by then, they're likely to be dealing with the consequences of the sun's aging long before the final settling of galaxies. One of the most human parts of this story is thinking about home. When we ask, how large is Andromeda? We're not just being curious about a distant pinprick of light. We're asking about the size and shape of a future home, how big the sky will become, how many neighbors we'll have, what kind of stellar neighborhood might cradle future civilizations. A merged Milkomeda, that's one popular nickname people use, would be more massive, with a deeper gravitational well and a halo that extends farther than either current galaxy. The density of stars in the central regions could increase. The overall shape could become smoother and less structured, and pockets of new star formation could light up for hundreds of millions of years. There's also loss. The process will eject some stars entirely, flinging them into intergalactic space where they'll drift alone. Planets could be stripped from their systems, moons tugged loose, orbits destabilized. The night sky for any survivors will be both stranger and more spectacular. New constellations forming over geological timescales. The familiar Milky Way band altered beyond recognition. A bright, twisting river of Andromeda light, growing and then merging into a single, more diffuse glow. If you let it sit for a moment, that future collision becomes a deeply personal cosmic narrative. It's the story of being rearranged by forces far larger than any of us. Yet it's also about continuity. The atoms in our bodies were forged in previous generations of stars. Future stars born in the wake of this merger will seed new chemistry, planets, and perhaps life. The galaxy that follows will be a different container for everything we are tied to, a new address stamped onto the cosmic map. It's a reminder that change on a grand scale is part of how the universe evolves, and that even seemingly violent processes can be part of a larger cycle of destruction and creation. Astronomers model this future using supercomputers and observations of other interacting galaxies. Those simulations give us movies of the dance, graceful streaks of stars, bursts of blue where gas converges, a final rounded silhouette that replaces the twin spirals. But even the best simulation is, in the end, a way to imagine our future. It helps us translate the quiet mathematics of gravity into a visual, tactile story we can relate to. So when you look up at the faint smudge of Andromeda with your own eyes, or through a small telescope, allow a little awe. In billions of years, that smudge will be a visitor at our doorstep, not a threat in the cinematic sense, but a cosmic partner reshaping the sky. The question of how large Andromeda is folds into a bigger question. What kind of place will the universe carve out for us next? And if we ever become travelers in space and time, maybe we'll choose where to settle in that grand remade home. So what happens when you take those impossible numbers, the hundreds of thousands of light years, the trillions of stars, the slow drift of galactic halos, and press them up against the shape of a single human life? At first it feels like a mismatch. Our days are measured in coffee cups and commutes, in birthdays and to-do lists. The galaxy is measured in ages that would eat 1,000 human generations for breakfast. It's tempting to shrug and say, those scales are too big to matter. But there's another way to hold those numbers, one that doesn't flatten them into insignificance but folds them around us like a kind of quiet comfort. Think of yourself as both small and deeply embedded. The galaxy is so large it hardly notices the flicker that is your life. And yet, in a very literal sense, you are a child of that enormous system. The iron in your blood, the calcium in your bones, the oxygen you breathe, those atoms were born in the furnaces of older stars that once lit up this same galaxy. You are made of the same story the galaxy tells. There's something grounding about that. The idea that your daily anxieties, your small victories, your messy relationships are all taking place inside a story that has been unfolding for billions of years. When astronomers say Andromeda is wider than the Milky Way, or that its faint halo reaches toward us, they're not just talking about distances on a chart. They're saying the universe is deep and continuous. Your life is a thread in a tapestry that stretches farther and lasts longer than any single human plan. That perspective doesn't diminish the value of what you care about. On the contrary, it can make the things you do feel more precious. When you hold the hand of someone you love, that moment is a tiny, intense event set against a vast backdrop. The scale shifts the weight, but not the meaning. Imagine looking at a candle flame close up. It's fragile, bright, immediate. Now zoom out until that flame is one of many in a dark field. The fragility is still there, but it becomes part of a larger, quieter beauty. There's also a very practical, almost liberating consequence to this cosmic perspective. Our personal dramas, missed promotions, awkward conversations, plans that fall apart, shrink in proportion to the time scales and distances involved. That shrinking doesn't mean they aren't important. It means we can look at them with a little less heat, a little more clarity. Problems that felt all-consuming yesterday can look like bumps on a map when you realize the map itself is almost impossibly large. But remember, size can be comforting and unsettling at the same time. There's a strange humility that comes from knowing the galaxy will not rearrange itself for your convenience. It goes on, indifferent to schedules and status updates. For some people, that can be hard to stomach. How can anything matter if it's all so tiny to the cosmos? For others, it's an opening. If the universe doesn't care about your every move, you're freer to define what matters to you, to choose kindness, creativity, care. You don't need cosmic approval to be meaningful. And there's another layer: continuity. The fact that the galaxy is this vast, deep thing means your life is part of a long chain of cause and effect. The atoms that make you were once inside a star that exploded, scattering the raw materials for life. Those atoms became shells. Shells became soil. Soil became plants, and plants became the chemistry of your body. That's a humbling, almost sacred lineage, one that connects you not only to distant stars, but to every person who has ever touched this planet. We can also use scale to reframe how we think about responsibility. When we understand that our planet, and the life on it, are woven into a much larger context, small actions start to look consequential in a different way. You can't single-handedly control the galaxy, but you can influence the patch of it you live in, the conversations you have, the way you treat other people, the choices you make about how you live on Earth. Those choices ripple outward, not to rearrange galaxies, but to shape the world the next generations inherit. And finally, there's a kind of companionship in the cosmos. When you look up and know that the same processes that made you are playing out across that vastness, stars being born, stars dying, halos of matter drifting and reaching, That knowledge can feel like a soft friend at your shoulder. It doesn't solve loneliness, but it reframes it. You're not isolated. You're integrated. You exist in a universe that is both indifferent and yet, through the chemistry of stars, deeply implicated in your being. So when the numbers start to blur, hundreds of thousands of light years, trillions of stars, let them do two things for you. Let them remind you of your smallness in scale, which can bring humility and perspective. And let them remind you that smallness isn't emptiness, it's participation. Your life is tiny by cosmic measure, yes, but it's also one of the universe's ways of looking back at itself. That thought is at once comforting and galvanizing. Comforting because it connects you to a grand, ongoing story. Galvanizing because it hands you a role in how that story continues. With that in mind, let's move from the comfort of scale to something even stranger: how galaxies actually interact with each other, and what that means for the future of our own cosmic neighborhood. So how big is Andromeda? A bright disk over 100,000 light-years wide, wrapped in a faint halo stretching hundreds of thousands more, and cloaked in dark matter nearly 1,000,000 li across. 1,000,000,000,000 suns scattered through enormous emptiness, a city of light with its own satellites, its outskirts brushing ours. Lying in your small room on a small world, breathe slowly, calm. Picture two star islands facing each other and let your thoughts drift between them until sleep arrives.